evening everybody. Today we will just continue the classification of the ligands. In the first part we have seen that how we can classify the different ligands in terms of their denticity, that means the number of donor atoms. Now we will see that these ligands can be further classified in terms of the nature of the donor atoms, which is very important. So, we can have these nitrogen based donor atoms. That means, what we have seen in the most simple one which comes to our mind is the simple ammonia molecule, and which is also a monodentate ligand. Then we can have the bidentate ligand based on the same nitrogen, which is ethylene diamine. So, one is that nitrogen based ligands, then we can have the oxygen based one. So, oxygen based ligand, the simplest possible as monodentate we have seen is the water one. Then we can have different types of other bidentate ligands like that of catechol and others. So, these are the simple possible bidentate ligands where we can have the nitrogen donor atoms or oxygen donor atoms, and at the same time we can also have the combination of these two. So, the combination of these two we can get for the simple amino acid glycine. This glycine, when binds to a particular metal center, is not a symmetric one, and also it is a mixed donor type, nitrogen and oxygen donor type. Then we can have the sulfur donor, then we can have the phosphorus donor and also the carbon donor. That means, when we have the carbon donor ligand present, we consider that we can have the corresponding metal carbon bond. So, carbon donor ligand can give us a system where we can have the metal carbon bond, and this metal carbon bond from that of our simple compound tetracarbonyl nickel 0 is a very important class of compound which are also known as the organometallic compound. So, all these ligands, when they are present in a typical backbone, and also we see that in some cases if X is the typical donor point and we can encircle all the 4 donor atoms like this, and we can put the metal center at the center, and we get a bigger cyclic ligand, and this particular cyclic ligand we can consider it as a macro cycle, it is a bigger cycle. So, this is the macro one. So, macrocyclic one. So, it has also some important role to play, and its biology also it is very well known. So, we can have this again, that means it can have nitrogen, it can have oxygen, it can have sulfur, or it can have the phosphorus donor atom, and which binds to the metal center. So, depending upon the nature of the donor atoms and the corresponding skeleton, the structure of the ligand system, we can have the different types of metal complex. So, in this class of the classification of the ligands second part, we will see the first example which is nothing but 3 pyridine rings attached together from the ortho position of one pyridine ring to the other ortho position, and again another ortho position of the nitrogen to the third ring. So, this we can see, we can consider this sort of ligand what we have earlier seen, which is has similarity with the ammonia. So, ammonia lone pair was utilized for the bonding to the metal center. Then we see that the pyridine lone pair also can be donated to the metal center, and if two of the pyridine donor atoms are present side by side, we get the bipyridine ligand, which is abbreviated as BPY. So, BPY is also a neutral one, neutral NN donor bidentate ligand, and when it binds to any metal center, we can have like ethylene diamine. If it is a bis compound, we get a bis compound of this type, but it is compared to the ethylene diamine backbone, it has more a rigid backbone. So, the property, the catalytic activity and all other things would be different compared to the corresponding ethylene diamine molecule. Similarly, if we can go for the third one, that means BPY backbone plus another PY, we get the corresponding ligand, which is known as terpyridine. So, this is our terpyridine ligand, where we see we can have 3 nitrogen donor atoms and which are close to each other. So, if we put metal center over here, so we get one particular side with the attachment of 3 nitrogen donor atoms. So, if this terpyridyl we can consider as N, N, N. So, it is N, 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 N3 type of tridentate ligand, and all these nitrogen donor atoms are pyridine based. So, if we have the metal ion like palladium-2 plus, so palladium-2 plus will bind with these 3 nitrogen atoms, and if we start to make this compound from palladium chloride, so one PDCl bond would be there, and roughly speaking the corresponding geometry of the compound would be square planar with 3 palladium nitrogen and 1 palladium Cl bond. So, we basically enclose the 3 donor points from one side for a square planar compound, and if it is a typical octahedral compound, so if the geometry is different, is octahedral in nature, then we can have the 6 positions for coordination, and these 3 coordinations now can be occupied, since it is a very rigid one. So, only one type of binding is possible, and one most important compound is the ruthenium-2, which can be very easily made with 6 ruthenium nitrogen bonds, and we can write down this compound when these nitrogens are terpyridine as ruthenium terpyridyl bis terpyridyl compound, and if the ruthenium center is in the +2 oxidation state, it is the +2, and the corresponding salts can be PF6, can be perchlorate or anything else. So, this sort of ligand is also very important because the photophysical and other properties for these ruthenium terpyridyl compounds are very rich. They can go for electron transfer behavior, it can be oxidized from bivalent to the trivalent state, and sometime in the excited states their electron transfer properties are different. So, this is one type of such ligand, is the tridentate one based on only pyridine donor atoms. And related to these, just now we have seen that if we can have a bigger cyclic ligand, we call it as a macrocyclic ligand. But if the cycle is not so big, it is little bit small, and if we can have only 3 nitrogen donor atoms, and those are all secondary nitrogen donor atoms, that means functions are NH. So, these nitrogen lone pairs from this nitrogen to this nitrogen to this nitrogen are all available to bind to the metal center. So, binding of this tridentate N3 type of ligand would be completely different from this binding, because this is basically when binding to the palladium or platinum center, it is going from one particular side, and only 3 of those sides are bound by these 3 nitrogen. But compared to these, the molecule which is known as triazacyclanonane. So, triazacyclanonane, or abbreviated as TACN, this TACN ligand will bind in a different mode to the metal center, but it can also satisfy the 3 donor points. So, binding to any metal center can provide us 3 metal nitrogen bonds, the first bond with this nitrogen, the second bond with this nitrogen, and the third bond with this nitrogen. So, if we can make the kappa 3 TACN compound of copper chloride, which is well known as a catalyst for hydrolytic cleavage of phosphodiester bonds of DNA. So, it has some biochemical reactivity for the esterase activity. So, esterase activity can only be shown for this sort of ligand, where the binding of these compared to any other tridentate ligand is completely different. What we see in this particular case is that when we have bipyridyl or terpyridyl type of ligand, we can simply say that terpyridine is there, and which is providing us 3 nitrogen donor atoms, and they are forming 3 bonds in one particular plane. And if the charge is satisfied by 2 chloride binding, it would be the corresponding copper terpyridyl Cl2 molecule, which is copper terpyridyl Cl2. So, the structure of this particular molecule is completely different, because what we have seen that in case of palladium or any other square planar molecule, the nitrogens are binding through these points, and if we have copper, so this is the Cl and this is another Cl. So, it is square pyramidal. In geometry. So, why we are classifying all these ligands in different categories? Because if we go for the TACN ligand, we have 3 NH groups which are more or less in one particular plane and which are connected by ethylene backbone. So, this particular type of ligand cannot go for binding for this square pyramidal geometry. Instead, it can go for one particular face. So, if we have a triangular face of one side of the copper, so if this is copper, so this is one NH, this is second NH, and this is third NH of the tacane. So, tacane is going to bind to the copper center, and we have 3 copper nitrogen bonds, and we have 2 such chlorine bonds to copper also. So, the geometry of this molecule is completely different to that of this one, and is a very useful molecule for showing the corresponding phosphoesterase activity. So, this particular one, that means this particular phase, it is basically a phase it is occupying, which is trigonal. So, one particular phase is the trigonal phase of the copper center, and 2 other positions are free. So, all the reactivity pattern for the DNA hydrolysis or any other thing can be achieved from the other side. Similarly, if a compound like manganese or anything which basically supports the octahedral geometry, when it supports the octahedral geometry, we can have one tacane from below and another tacane from above. So, these are all the nitrogens NH, 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 and NH. So, these are forming 6 such bonds. So, is one phase, one trigonal phase is occupied, and another trigonal phase is also occupied for the coordination of 2 tacane molecules to the manganese center, giving rise to same octahedral geometry. But here now both the sides, that means both the trigonal faces are occupied. So, it is basically capped from the top as well as capped from below, and in this particular geometry its reactivity pattern should be less. So, it is showing the esterase activity when it is bound to copper center, and we can prepare also it very easily, because this cyclization thing is also we can have this one particular part is the ethylene diamine part, then another ethylene diamine. So, it is diethylene triamine part. So, diethylene triamine part, if it is connected by another ethylene backbone, we get the tacane, and during the preparation of these we get the corresponding isolation of the tacane compound as its corresponding hydrochloride salt. So, is dot 3 HCl is written. So, is the tacane hydrochloride salt we can have. Then simple metal salt like copper chloride is used to react with this, and in solution which is alkaline with respect to sodium hydroxide. So, sodium hydroxide is given the copper 3 tacane copper chloride compound, where copper 3 gives us the 3 points of attachment like mu nomenclature to the tacane to the copper center, then water and then NaCl is coming out. So, we nicely and very simple way we get the corresponding dichlorocopper tacane compound. So, if we just proceed further, where we can have another long linear chain of ligand is that diethylene triamine, which is known as triene. So, like that where we have that N3 type of ligand, now we can have diethylene triamine, triethylene tetraamine, sorry, the triethylene tetraamine molecule using this backbone of diethylene triamine, which is one more extension of the ethylene backbone. So, straight away we can see now that if since we have 4 nitrogen donor atoms and all 4 if they are utilized to bind to the metal center, we get a tetradentate ligand. So, very simple way we get the corresponding triene is tetradentate, and this one is the N4 ligand, and this N4 ligand can be further derivatized because we have the NH2 at the 2 ends of the backbone, and these NH2 ends are very well known for the formation of CIP bases with say 2-hydroxy benzaldehyde or salicylaldehyde. So, not from the ligand itself, but for the triene. So, triene when reacts with 2 molecules of salicylaldehyde, we get the corresponding hexadentate ligand, which is very useful ligand. So, in a simple reaction of triene with salicylaldehyde, we get N4O2 type hexadentate ligand, and this hexadentate ligand can bind very nicely with any 3D metal ion or 4D metal ion or 5D metal ion also, say with Ni2 plus, giving Ni2 plus as the corresponding perchlorate or acetate salt as simple NiL2 plus complex, where all the 6 positions in octahedral fashion, in this fashion where the manganese will be substituted by this particular nickel center. So, octahedral nickel compound can be obtained from a simple condensation product of triene and salicylaldehyde, and this particular one, this ligand which has a corresponding imine backbone. So, at the 2 ends, this particular end and this particular end, we have the imine backbone. So, this particular ligands are also known as the corresponding CIP bases or the CIP base ligand. So, this particular amine, that means triethylene tetraamine, is very useful one when it is in the pure form, or it is condensing with some other aldehydes like salicylaldehyde or pyridine 2 aldehyde also. When it can be condensed with pyridine 2 aldehyde, it can give us the similar type of CIP base ligand, but the donor atoms all will be nitrogen. So, it would be a N6 ligand binding to any octahedral metal ion. This is another form of this particular N4 ligand, which is known as tris 2-aminoethylamine. So, this is the central nitrogen which is connected by 3 aminoethyl backbones. So, this we can consider as a derivative of ammonia molecule, where ammonia nitrogen is bound to 3 hydrogen atoms, but instead of 3 hydrogen atoms, now we can have 2 aminoethyl groups attached to the nitrogen, and these nitrogens all can give rise to the corresponding coordination to the metal center. So, this is a linear tetradentate ligand N4 type. This is not a linear one, but this is a capping one. So, one particular end can be capped with use of this particular train ligand. So, this is abbreviated as train, and we can have further ship base condensation. We can go for the ship base condensation at the free NH2 ends of this. Once that condensation is taken place with salicylaldehyde, we can have a heptadentate ligand, because we are further functionalizing this nitrogen to NO, this to NO, and this nitrogen also to NO. So, 3 such NO donor atoms gives us 6 donor points and this central nitrogen. So, that would be basically a heptadentate ligand in our hand if we go for the corresponding ship base condensation with 3 molecules of salicylaldehyde. So, if we just simply use this particular train ligand, the tris-2-amino ethylamine ligand, and when it is binding to any metal center. So, this is the central nitrogen, this nitrogen is bound over here. So, this is one other amino ethyl backbone, this is the second amino ethyl backbone, and other one is the third one. So, if this particular center, if this metal center is copper center and copper chloride is reacting within this fashion such that we can have one copper chlorine bond only, and all other 4 positions are occupied by the nitrogen donor atoms of the amine. So, we basically get coordination number of 5 around the metal center, which is copper, and charge is neutralized if this is only one copper chlorine bond. So, it has a different geometry compared to the corresponding TACN copper Cl2 compound, and the geometry is also quite different since we are occupying this particular nitrogen, which is the tertiary nitrogen, and this tertiary nitrogen can show some long metal nitrogen bond. So, the overall geometry of this particular system is trigonal bipyramidal. So, this trigonal plane, the basal trigonal plane is formed from 3 NH2 groups, they are all similar. The bonding property of these 3 NH2 groups are of same type, and these 3 NH2 groups are directly attaching to the metal center, say copper 2 plus, and they remain in a single plane. So, this is our trigonal plane, and the bipyramidal part is the trigonal this trigonal bipyramidal part is that one nitrogen from the central nitrogen of the amine, this nitrogen, and another one can be Cl, can be Br, or can be F also when we are reacting with copper chloride, copper bromide, or copper fluoride. So, we get a TBP geometry. So, very nicely we can have using this sort of ligand. So, ligand can create a typical geometrical environment around the metal center, which is trigonal bipyramidal, and when little bit reorganization is taking place, and if the center is not copper, but if it is nickel or if it is iron or cobalt, which has a preference for octahedral geometry, this particular metal center can give rise to 6 coordination positions, 4 from the ligand and 2 from the halides. This can be chloride, this can be bromide. So, what happens that this particular geometry has some distortion, because this particular accommodation of X is required. So, when this NH2M NH2 bond in this molecule was around 120 degree, this bond is around 120 degree, which is reduced to around 90 degree for a octahedral geometry. So, squeezing of this NH2M NH2 bond is required for the movement of the trigonal bipyramidal geometry to an octahedral geometry, and which is also possible if we move from one metal center to other, which has a typical preference for octahedral coordination. Then we can have another type of ligand which is very useful in organic synthesis, which is box type known as box also, which is abbreviated as box, which is bis-oxazoline type of ligand. So, bis-oxazoline is abbreviated. So, bis-oxazoline type of ligand is abbreviated as box because this is the oxazoline ring. So, if we have the methylene spacer here, this is the CH2 group. So, if we have the CH2 spacer over here and two oxazoline rings, oxa and aza in the same ring. So, two oxazoline rings are attached on the two sides of the methylene ring. So, which is a tetrahedral carbon. So, we can specify the corresponding nitrogen geometry, since this is also a typical bidentate type of ligand, but the geometry pattern is completely different compared to ethylene diamine or bipyridine. So, this gives rise to some N donor type of bidentate ligand, because the free rotation around this carbon-carbon bond or this carbon-carbon bond can bring rise to the oxygen also, but the preference for this nitrogen coordination, which is also dependent on the substitutions R on this 5-membered ring, is also required, and which is fixing this particular geometry, and this ligand has a preference for nitrogen coordination to the metal center. So, from this methylene backbone, the CH2 backbone, if we just move to a pyridine backbone, and the pyridine ring can be utilized for functionalization from its 2 and 6 positions with the use of two oxazoline rings. So, we get a P-box ligand. So, P-box ligand is a typical tridentate ligand, but this particular ligand is a different one compared to the pyridine ligand, because the geometry is different, its coordination is different, and the corresponding metal nitrogen bond distance and the corresponding strain on the ligand is also completely different. So, several coordination complexes can be made with this particular type of ligand for seeing whether they are catalytically active or not. Some useful compounds on manganese or on copper or bis-oxazoline ligands are extremely useful in the different types of asymmetric synthesis. So, in organic chemistry, the asymmetric synthesis has been benefited a lot with the use of this sort of ligands, where the typical geometry has been adopted compared to the bipyridyl or terpyridine type of ligands. So, these are therefore one other group of ligands. Then we can go for a typical macrocyclic ligand, where we can have 4 donor atoms, and if they are nitrogen bearing, as we have defined earlier, that these nitrogens can be connected very easily, and when we connect we get a complete cyclic geometry, and this can be derived if these are all NH, like getting taken from diethylene triamine. So, this can be obtained if we consider the triene backbone. The triene was NH2, NH, NH and NH2. So, only thing that this particular backbone has to be connected. So, if these two ends we can connect, say by dibromoethane or say glyoxal, using these two molecules. So, we can get a cyclic product, and this cyclic product is related to the taken molecule, but is of bigger size. So, this cavity size is important. This cavity size will say what type of ligand can go and enter, whether it is Fe3 plus or Mn2 plus or cobalt 2 plus or 3 plus. So, this we get. So, if we have this only ethylene backbone for these, so all the 4 nitrogen atoms are connected by 4 ethylene bridges, then we get one particular type of ligand which is known as cyclane, which is nothing but 1, 4, 7, 10 tetra as a cyclododecane, which is like that of tacane, triaza cyclanonane, which is cyclododecane. So, which is having 8 plus 4, 12 atoms in the backbone. In tacane we have 9 backbone, that is why the nomenclature ends with the nonane end, this is dodecane end. So, when we find that how this particular geometry can bind, because these are all saturated CH2 groups, those are all tetrahedral carbon. So, when the tetrahedral carbon is tried to bind some metal center, this entire ring basically cannot be a planar one, but it is basically a puckered one, where we see that 4 nitrogen atoms, these NH groups, because NH groups, this is non nitrogen, this is second, this is third and the fourth one. So, all 4 nitrogen donor atoms are basically going towards the upward direction. That means, this nitrogen is basically a pyramidal one, because the third bond which is attached to this nitrogen is the NH bond. So, this is pyramidal, this is pyramidal. So, 4 pyramidal nitrogens are pointing towards the upward direction, and when these 2 adjacent nitrogens are in the upward direction, so you have the downward direction of the backbone, and which is trying to coordinate to the metal center. So, when we have a corresponding compound of zinc to cyclane, so zinc atom is basically sitting on this particular ring. In this particular cyclic ring, zinc atom is sitting over there, and one ethanol molecule is coordinating, fulfilling the 5th coordination site for the zinc atom. So, this ligand is providing 4 donor atoms, 4 nitrogen atoms are provided by this ligand, and the 5th one is by the corresponding ethanol. So, this particular geometry is much more flexible, and we have a puckered geometry for the ligand system. So, this can be found from the reference of inorganic chemistry by American Chemical Society. Then, if we just increase the backbone from ethane to propane, that means CH2 whole 2 to CH2 whole 3, that means we have a little bit relaxed macrocycle, which is a different one, and we call it as a cyclone. So, cyclone ligand is related to the previous one, but it has a different cavity size for the coordination to the metal center. And we have all isomeric forms we can have, since all the NH groups can be substituted by N-methyl or N-ethyl. So, depending upon the positioning of 4 methyl or 4 ethyl groups, we can have different types of isomers, because we have seen in the previous example that when the nitrogen is in the pyramidal site, we have the hydrogen in the backbone there, and this hydrogen is now substituted by methyl and ethyl group. So, either this methyl group can be up or can be down. So, when 4 of them are up, we have this geometry, when 3 of them are up this. So, in this sequence we can have all these possible isomeric forms when simply the nickel is bound to cyclone. So, we have the corresponding square planar complex, and metal cyclone complexes are all isomeric in nature, depending upon the corresponding orientation of the N-methyl or N-ethyl groups. Similarly, if we just simply go from nitrogen to oxygen, which is not so strongly coordinating to the metal center, but we can have very poorly donating ligand system, but which is cyclic in nature, like the binding of the ether. So, if we have the ether, say diethyl ether, and if we just compare this diethyl ether with that of our water molecule. So, we all know this water molecule. So, these lone pair of electrons on ether and water molecules are available for coordination, but this binding is not so strong, which is weak coordinating to the metal center. So, when one ether is available, we get a corresponding coordination to one particular metal center, but if we can have more than one such ether group, such as this one, this can also go and bind to the a typical metal ion. So, if we now complete the cycle by 3 or 4 donor atoms, 4 ether like of this thing, we get a cyclic system, where these cyclic systems are known as the corresponding crown ethers. So, these are another group of ligands in this particular class. They are crown ether ligands, because they are very useful and they can bind to metal ions like sodium, potassium and other very weakly, like that of the coordination of water molecule. So, when we have 4 oxygen atoms and the backbone is completing with 12, that means 8 carbon and 4 oxygen, so it is 12 C4. Similarly, if we change to 5 oxygen, it is C5, 18 C6, and if we have 2 benzo backbone, we get dibenzo 18 C6 crown ether, and if 1 oxygen is replaced by NH, we get diaza 18 C6, which is analog of this 18 C6 molecule, but 2 oxygen donor atoms of the ether are replaced by 2 aza functions of NH. So, this has been a very useful molecule for binding to the potassium ion, the alkali metal or alkaline earth metal, which how we just basically transport, particularly in the biological system, from cell membrane from one side to the other. So, we need some selective ligands for potassium binding, which we are not discussing in detail for coordination chemistry. That means the chemistry related to the transition metal ions, but the binding of these alkali and alkaline earth metal ions are very important. So, when potassium ion is coordinating with 18 crown 6, we have this particular one which is 18 crown 6. So, potassium is sitting over here and 6 oxygen atoms are binding to this particular potassium, because this cavity size is matching very much with that of our potassium ion. And this particular geometry, because this particular geometry is also fulfilling the corresponding Packard movement from one side, this is up, this is down, this is down, this is up, to make a corresponding 3-dimensional structure. That means the coordinating geometry around this potassium is octahedral in nature. So, like that of our other transition metal ions, which are based on a typical octahedral geometry, potassium is trapped within the crown ether by such 6 oxygen donor atoms related to that of the coordination of water molecules. So, this oxygen can also be substituted by sulfur, which gives rise to 1,4,7 trithiacyclonone, like that of our TACN molecule, where all the sulfur groups were occupied by NH functions. Then this is also a related ligand compared to this one, which is a cyclic one, but this is an acyclic one bearing 2 sulfur and 1 oxygen donor, which is well known for binding the heavy metal ions. And during World War II and all this case time, this has been developed as which is a dimercaprol or British antiloicite molecule, we call it, because it binds heavier metal ions like cadmium, zinc, mercury and all these, which are very much poisonous. Even if it goes to our body also, it has some detrimental effect on our body. So, we want to eliminate by using this sort of ligand or this type of ligand to coordinate to the metal center and coming out from the body. Similarly, this sulfur binding to the heavy metal ion can also be established through a other simple ligand which is known as dithiocarbamate. So, a sodium diethyl dithiocarbamate is another type of ligand where we take diethylamine. This is basically diethylamine, and when diethylamine is reacted with carbon disulfide in sodium hydroxide medium, we get the corresponding sodium diethyl dithiocarbamate ligand. And like this ligand, this also binds through these two sulfur atoms. So, these two sulfur atoms when binds to the metal center, it is basically providing the corresponding bidentate sulfur ligand to the metal center. So, S and S, if it is there, which is coming from dithiocarbamate, and it binds to the metal center through sulfur. So, SS bidentate ligand. So, SS bidentate ligand is our diethyl dithiocarbamate, and this diethyl dithiocarbamate we can see can further be categorized to binding to the different metal centers. Then another class of bicyclic ligand we can have. This is one other type of bicyclic ligand related to the nitrogen coordination and oxygen coordination like that of our crown ether. So, if we have 6 oxygen donor atoms from one side, so this is the cyclic backbone, and this is another kind, that means which is connected these nitrogen which were originally NH function. So, we have one cycle and this is another cyclic. So, this is basically a bicyclic ligand, and these type of molecules are known as cryptands, and these cryptands are synthetically prepared. It can be bicyclic or it can be also polycyclic. So, it is useful for binding a variety of cations, and it is also bidentate and polydentate in nature. So, is one half of this bidentate part can go to bind a metal center here. So, if all the 6 donor atoms are utilized for binding say one metal center, say potassium like crown ether. So, this potassium when it is centrally located, it binds to 6 oxygen atoms only, and these nitrogens are not utilized for any coordination to the metal center, because already we are having this particular nitrogen which is pyramidal in nature. So, if the pyramid is like this, the lone pair is available on the other side of this nitrogen. Similarly, the lone pair is also available from this point to the other side of the ring. So, these two nitrogens will not be utilized for coordination to the metal center. Instead, we are providing in a different way 6 donor atoms like 6 oxygen atoms to the metal center in a bicyclic structure. So, these are all cryptand molecules, and they basically encapsulate, they trap the metal ion very nicely within this particular cavity. So, apart from this macrocyclic ligand, this is a bicyclic one which has a sphere like arrangement and which can trap the metal ion very nicely within this particular cavity. And this particular cavity also gives us this particular coordination. So, this nitrogen and this nitrogen, when it is puckered, this nitrogen is pointing towards this particular end, and when this nitrogen is pointing toward this particular atom, it is forcing to show some other interaction. So, you can see that in this structure, this particular coordination for this metal center is from 6 oxygens as well as 2 nitrogens. So, it is 8 coordinated. So, bigger metal ions like lanthanides and all can be very nicely placed within the cryptand pocket. So, bigger as well as we can put potassium also. So, starting point when we synthesize the potassium salt of this can be made, which can be exchanged with the other lanthanide ions for the coordination within this particular cryptand sphere. So, like that of our acetyl acetone. So, if we have the substitution for the acetyl group by the 2 phenyl rings, in this particular case of these molecules, we will see that acetylacetone can be moved from one particular point to the other, where we have more rigid structure, more rigid backbone, which is known as benzoyl acetone. So, this benzoyl acetone having this pH backbone, and it can bind to the metal center in a bidentate fashion. So, these two donor points through enolization. So, this will be OH through enolization by taking one hydrogen from this CH2 group to make it a OO mononegative bidentate ligand like acetylacetone. Similarly, people are also trying to make a newer type of ligand by substitution. Since the phenyl ring has been introduced like benzene ring, we can go for substitutions in the para position of this phenyl ring. So, substitutions in the para position of these phenyl rings can give us some useful information, because this molecule is not only useful for binding to the metal center through these two oxygen atoms, but it can be useful for some other activity like making this molecule, and is known as the corresponding avobenzone. Avobenzone is nothing but butyl methoxy dibenzoyl methane. So, is the butyl function, and another is the methoxy substitution. So, two substitution at two ends of the phenyl ring, particularly the para position by butyl function as the methoxy function of dibenzoyl methane, can be useful because it is soluble in non-aqueous medium, is soluble in oil and any other cream material, is very useful ingredient for use as a sunscreen lotion, because it absorbs the full spectrum of UVA radiation. So, the range of UV ray radiation can be absorbed by this particular molecule, and sunburn due to UV exposure can be stopped, and this molecule is therefore is a useful ligand, but it has found that it can have some other application as well. So, another type of ligand is also well known, is also another class for the chelating one, which is the Pincer Ligand, which binds tightly to three adjacent coplanar sites. So, if we have three adjacent coplanar sites like that of our terpyridine type of ligand. So, if we have one donor point and another donor point and the third donor point. So, three such donors, if they are available, and if these three are adjacent coplanar sites, that means one plane and the other plane are basically giving rise to a basically a planar tridentate arrangement, not that it can move to some other plane, and usually it binds in a meridional configuration. That means in plane configuration is available for binding to the metal center. So, this particular ligand is one sort of this example of the Pincer ligand. This is another Pincer type of ligand. So, like that of our terpyridine ligand, what we have seen earlier, that terpyridine ligand have one pyridine here, second pyridine here and third pyridine here. Instead of that, now we can have in two ortho positions of the pyridine ring, the one as the phosphine donor and another as the nitrogen donor. So, NN diethyl donor from the right hand side and phosphine donor with butyl groups, tertiary butyl function, which is the bulky group. So, if we put bulky groups around this phosphorus and two other bulky groups around this nitrogen, we will see that we are forcing this particular plane, which is a 5-membered chelate ring around ruthenium, and this is also another 5-membered chelate ring on the other side, but this is bearing phosphorus and this is bearing nitrogen, and if they are pretty close to each other and if the planar arrangement is such that it is very tightly bound. So, what we find, that we find a typical geometry for this ruthenium center, where we are providing a tridentate coordination around this ruthenium center. So, basically what we get this nitrogen, this is another nitrogen, and this is the phosphorus. But the size of these, that chelate ring size is very important, which is basically this sort of thing we can have when we have this 2 carbon spacer. If we can have, so 2 carbon spacers is more relaxed. So, what we get, we basically this particular form, that means we have this phosphorus also and the 2 carbon spacer and this nitrogen. So, this is basically a 5 member ring, and if we can go for other type of ring like this Pincer one, in case of Pincer ligand, we can have these as the corresponding planar part, and this planar part basically giving the corresponding meridional configuration, and we have 2 positions available which can be occupied by x and y. It is not that one tridentate hub and we can have another tridentate hub around this ruthenium such that we get the octahedral geometry. Instead of that, we can have a 5 coordinated geometry if we have the ruthenium. Similarly, if we go for iridium, when pyridine is substituted by the benzene ring, we have the metal carbon bond. So, it is basically a typical example of organometallic compound, and 2 hydride bonds are also there, and which is giving rise to a trigonal bipyramidal geometry. So, these are very good catalysts in turn. So, Pincer ligands are very useful for their catalytic activity, because we can use some of these positions for useful catalytic activity, that we are not bringing any other ligand, but we will go for only the substrate binding and the reagent binding from these 2 positions. Here also the substrate binding and reagent binding by removal of this carbon monoxide and hydrogen. Okay. Thank you.